Basic QED processes require the calculation of traces of gamma matrices. To help us with the calculation of these traces, we will first introduce a new gamma matrix, the gamma 5 matrix. Notice that there is no gamma 4 matrix. In the hierarchical representation of the gamma matrices, you can show that gamma 5, so I, gamma naught, gamma 1, gamma 2, gamma 3, is equal to this 4x4 matrix, where each individual component, 0 and 1, are the usual 2x2 matrices. From there, you can also easily show that gamma 5 squared is just the identity, and that gamma 5 anti-commute with all the other gamma matrices. So let's start with a trace of a gamma matrix. So the trick is to multiply by the identity in the form of gamma 5 squared. Then we use the cyclicity of the trace. Then we use the anti-commutation property of gamma 5 with gamma mu. And gamma 5 squared is just 1. When something is equal to minus itself, therefore it has to be 0. So the trace of one gamma matrix is always 0. Let's now compute the trace of two gamma matrices. Here we will use the fact that the anticommutator of two gamma matrices is twice the metric, which was how we defined the gamma matrices. G mu nu doesn't contain any spin, and the trace is only acting on the spin degrees of freedom. So as far as spin is concerned, this term only is the identity, which is a 4x4 identity matrix, and therefore the trace of this identity is going to give us a factor 4. We now use the cyclicity of the trace. We can show in a similar way that the trace of 3 gamma matrices, or more generally the trace of an odd number of gamma matrices, is always 0. And the trace of 4 gamma matrices